The morning fog clung to the English countryside like a burial shroud, as Captain Matthias Cornelius crouched beside the twisted wreckage of what should have been a dead machine. September 23, 1943. Royal Air Force Station Tangmere. The captured Fw-190 lay on its belly in the maintenance hangar, its propeller blades bent like broken fingers, cannon holes stitched across its wings, and yet the BMW 801 radial engine still turned over with a rhythmic purr that defied every principle of aeronautical engineering Cornelius had learned in his 12 years designing aircraft power plants. The German fighter had taken hits that would have sent any Allison or Merlin engine to the scrap heap, but this Bavarian Motor Works creation continued to function as if the laws of metallurgy were merely suggestions. Steam rose from cooling cylinders that bore scorch marks from 20-millimeter shells. Oil leaked from punctured lines that should have seized the entire mechanism within minutes, and still the massive 14-cylinder radial maintained compression across all its chambers. Cornelius pressed his ear against the cowling and listened to the impossible symphony of precisely timed combustion echoing through an engine that had absorbed enough battle damage to destroy 3 Allied fighters. The acrid smell of cordite and aviation fuel mixed with the metallic tang of cooling steel as he traced his fingers along impact craters that penetrated deep into the engine block without causing catastrophic failure. His commanding officer had ordered him to catalog the wreckage and prepare it for shipment to Wright Field for standard intelligence analysis. But standing there in the dim hangar light, watching condensation drip from bullet holes that hadn't killed this remarkable machine, Cornelius made a decision that would transform Allied aviation forever. He was going to tear this engine apart piece by piece, rebuild it from memory, and discover exactly how German engineers had achieved the impossible. No one in the 8th Air Force knew that one captain's disobedience that morning would rewrite the mathematics of aerial survival and bring hundreds of bomber crews home alive. Captain Matthias Cornelius had grown up in the small industrial town of Bridgeport, Connecticut, where his father operated a precision tool shop that supplied parts to the emerging aviation industry. As a boy, he had spent countless afternoons in that shop, learning to read the microscopic tolerances that separated functional machinery from scrap metal, developing an intuitive understanding of how stress and heat and vibration could destroy even the most carefully crafted mechanisms. His hands learned to recognize the subtle difference between properly tempered steel and metal that would fail under pressure, knowledge that came not from textbooks, but from years of watching his father's calloused fingers test the spring and flexibility of every component that passed through their workshop. When the Depression struck and orders dried up, young Cornelius had watched his father adapt by reverse engineering broken machinery, studying failed components until he could reproduce them with improvements that prevented future breakdowns. That lesson in applied persistence would prove invaluable in ways neither father nor son could have imagined. After graduating from the Worcester Polytechnic Institute with a degree in mechanical engineering, Cornelius had joined Pratt & Whitney as a junior designer, working on the radial engines that would power the new generation of military aircraft emerging from American factories. His colleagues respected his methodical approach to problem solving and his ability to visualize complex mechanical relationships, but they also noted his troubling tendency to question established procedures when his instincts suggested better alternatives. He had earned both commendations and reprimands for unauthorized modifications to prototype engines, improvements that increased reliability but violated strict development protocols. When war came and the Army Air Forces desperately needed engineers who understood combat power plants, Cornelius had volunteered for overseas duty, hoping to apply his skills where they would make the greatest difference. His superiors appreciated his technical expertise, but worried about his inclination to pursue unauthorized research projects that diverted resources from approved programs. He had no idea that soon those instincts would be all that stood between discovery and the continued slaughter of Allied air crews. The air war over Europe had become a grinding battle of attrition, where mechanical reliability often determined who lived and who died. By the autumn of 1943, American bombers were penetrating deeper into German-controlled territory, facing increasingly sophisticated defenses that included not only fighter aircraft, but also concentrated anti-aircraft artillery that filled the sky with exploding steel fragments designed to shred aircraft engines and control surfaces. The mathematics of aerial combat had evolved into a brutal calculus where slight advantages in engine durability could mean the difference between completing a mission and becoming another smoking crater in occupied France. Allied intelligence had documented disturbing patterns in combat reports that suggested German aircraft were surviving damage levels that would have destroyed comparable American or British machines. Pilots reported seeing Fw-190s continue flying with visible engine damage, trailing smoke and oil, but maintaining sufficient power to escape or even continue attacking Allied formations. These observations contradicted everything Allied engineers understood about radial engine vulnerability, particularly the tendency of air-cooled power plants to lose compression and seize when cooling fins were damaged by shrapnel or machine gun fire. The captured Fw-190 at Tangmere represented the first opportunity for Allied technicians to examine this phenomenon in detail, to understand how German engineers had apparently solved problems that continued to plague Allied aircraft development. Standard intelligence protocol called for a preliminary inspection followed by shipment to the United States for comprehensive analysis, a process that could take months while Allied air crews continued to face opponents with superior equipment. The official orders were clear: catalog visible features, photograph major components, and prepare the aircraft for transport without conducting unauthorized examinations that might damage evidence. But as reports continued to arrive describing German fighters absorbing impossible amounts of battle damage, while Allied bombers fell from the sky with relatively minor engine hits, the urgency of understanding German technological advantages became increasingly apparent. The stakes were measured not in abstract engineering principles, but in the lives of young men who trusted their machines to bring them home for missions over hostile territory. Captain Cornelius spent the next 3 days following protocol, methodically photographing every external detail of the captured fighter, while suppressing his growing compulsion to examine the internal mechanisms that had allowed this particular machine to survive its encounter with Allied defenses. The aircraft had been forced down after a running battle with Republic P-47 Thunderbolts over the French coast. Its pilot killed by a lucky burst of .50 caliber fire that had penetrated the cockpit while leaving the engine compartment intact enough to maintain power for an emergency landing. Initial inspection revealed impact damage that should have been fatal to any radial engine, including direct hits to multiple cylinder heads, punctured cooling fins, and severed oil lines that had somehow sealed themselves sufficiently to maintain minimal lubrication. Cornelius documented each anomaly with growing fascination, noting engineering features that seemed to anticipate battle damage and compensate for failures that would have destroyed Allied power plants. The BMW 801 displayed a level of redundancy and fault tolerance that suggested German engineers had approached the problem of combat survivability with systematic thoroughness rather than the piecemeal modifications that characterized Allied development efforts. On the 4th day, as he prepared his preliminary report for transmission to Wright Field, Cornelius made a discovery that changed everything. While photographing the engine's accessory section, he noticed that several components appeared to have been manufactured using techniques that produced internal structures significantly different from comparable Allied parts. The magnification system of his analysis equipment revealed grain patterns in the metal that suggested advanced metallurgical processes, possibly involving controlled cooling rates or alloy compositions that were unknown to American industry. He realized that documenting external features would provide no insight into the fundamental innovations that had produced this remarkable machine. That understanding would require disassembly and detailed examination of internal components using techniques that would certainly violate his orders and possibly destroy evidence that might prove crucial to the overall intelligence assessment. As evening approached and the hangar grew quiet, Cornelius stood beside the captured fighter and contemplated a decision that could end his military career but might save countless Allied lives. His commanding officer had been explicit about maintaining the integrity of the evidence, but his engineering instincts screamed that the real secrets lay hidden beneath access panels that standard photography would never reveal. The unauthorized examination began just after midnight, when the guard rotation changed and Cornelius could work undisturbed in the darkened hangar. He had prepared meticulously, gathering tools and equipment that would allow him to disassemble major components without leaving obvious signs of tampering, planning each step to ensure that he could reassemble everything exactly as he had found it. The BMW 801 radial proved to be a masterpiece of engineering sophistication that revealed its secrets reluctantly, each removed component exposing new layers of innovation that contradicted accepted principles of power plant design. The cylinder heads, which should have cracked or warped under the thermal stress of battle damage, had been manufactured using a casting technique that distributed stress in ways that maintained structural integrity even when cooling fins were destroyed by shrapnel. Cornelius discovered that German engineers had embedded a network of internal cooling passages that provided redundant heat dissipation, allowing individual cylinders to continue functioning even when external cooling was compromised. The crankcase assembly revealed even more sophisticated engineering, with bearing surfaces that had been treated using processes that created microscopic oil retention cells, maintaining lubrication even when normal oil circulation was interrupted by combat damage. Each component told a story of systematic innovation, of engineers who had anticipated every possible failure mode and designed solutions that kept engines running under conditions that would have been fatal to Allied power plants. As the hours passed and Cornelius worked deeper into the engine's internal mechanisms, he began to understand that the German aviation industry had achieved breakthrough advances in metallurgy and manufacturing that gave their aircraft decisive advantages in combat survivability. The implications were staggering. Allied bomber crews were dying, not because of superior German tactics or superior pilot training, but because German engineers had solved fundamental problems that Allied industry had not even recognized. By dawn, Cornelius had filled 3 notebooks with detailed drawings and measurements, documenting innovations that could revolutionize Allied aircraft engine design if they could be reproduced using American manufacturing capabilities. But he had also committed an act of insubordination that could result in court-martial if discovered, and he faced the challenge of convincing his superiors that unauthorized research had uncovered intelligence vital to the war effort. The confrontation with Colonel Harrison Blackthorne came sooner than Cornelius had anticipated, when the base commander arrived for an unscheduled inspection and found him reassembling the BMW engine with obvious signs of extensive disassembly scattered around the hangar floor. Blackthorne was a career officer who valued discipline above initiative and who regarded unauthorized actions as threats to the chain of command that kept military operations functioning efficiently under the chaos of wartime conditions. He stared at the partially assembled engine, at the tools and components that clearly indicated unauthorized examination, and demanded an explanation for what appeared to be flagrant disobedience of direct orders. Cornelius realized that his career hinged on the next few minutes, that he needed to convince a traditional military commander that engineering discovery justified insubordination, that the knowledge he had gained was worth the risk he had taken. He began with the numbers, explaining that Allied bomber losses to engine failure under combat conditions were running nearly 30% higher than comparable German aircraft losses, that this captured engine represented the first opportunity to understand why German machines were surviving damage that killed Allied crews. Blackthorne listened with growing skepticism as Cornelius described metallurgical innovations and cooling system redundancy, clearly viewing technical explanations as elaborate justification for simple disobedience. The tension in the hangar became palpable as Cornelius realized that scientific curiosity and military discipline were on a collision course that could end his involvement in the war effort and doom Allied air crews to continued disadvantage against superior German technology. Then Cornelius made a desperate gambit, offering to demonstrate the principles he had discovered by modifying an Allied engine using German techniques, proving that American industry could reproduce the innovations that had kept this particular Focke-Wulf flying after absorbing fatal damage. Blackthorne remained silent for long minutes, weighing the risks of further unauthorized experimentation against the potential benefits of understanding enemy technological advantages. His decision would determine whether Cornelius's discovery remained buried in military bureaucracy or became the foundation for modifications that could save hundreds of Allied lives. The experimental program that emerged from that confrontation operated in absolute secrecy, with Cornelius working under direct orders from the highest levels of Allied command to reverse-engineer German innovations and adapt them for use in American aircraft engines. He was given access to machine shops and metallurgical facilities that allowed him to reproduce the manufacturing techniques he had discovered, but he was also warned that failure would result in immediate reassignment to duties that would remove him from any position where he could influence Allied aviation technology. The pressure was enormous. Hundreds of bomber crews continued to face missions over German-controlled territory while flying aircraft powered by engines that could not match German survivability standards, and every day of delay meant more young men would die because their machines failed when German machines would have continued flying. Cornelius threw himself into the work with desperate intensity, collaborating with the most skilled machinists and metallurgists available to the Allied war effort, pushing American manufacturing capabilities to reproduce innovations that German industry had perfected through years of systematic development. The first prototype modifications showed promising results in laboratory testing, with treated components demonstrating significantly improved resistance to the types of damage that typically destroyed aircraft engines under combat conditions. But laboratory conditions could not replicate the complex stress environment of aerial combat, where engines faced simultaneous challenges from altitude, temperature variation, vibration, and battle damage that tested every system to its limits. The real test came when modified engines were installed in operational aircraft and subjected to combat missions over occupied Europe, where German fighters and anti-aircraft defenses provided the ultimate evaluation of engineering improvements. Initial reports were encouraging. Aircraft with modified engines were completing missions after sustaining damage that would have forced earlier aircraft to abort or crash. Crews were returning from missions they would not have survived with standard equipment, and combat effectiveness was increasing as aircraft reliability improved. But Cornelius knew that statistical success had to be measured against the enormous cost of Allied bombing operations, that even small improvements in survival rates represented hundreds of lives saved and missions accomplished that might otherwise have failed. The breakthrough came during the spring of 1944, when systematic application of German metallurgical techniques began producing American aircraft engines that could match or exceed German performance under combat conditions. Cornelius had spent months working with industrial partners throughout the United States, sharing his discoveries with companies like Pratt & Whitney, Wright Aeronautical, and Allison Engineering, helping them adapt their production processes to incorporate innovations that had been developed by their German counterparts. The collaboration required unprecedented cooperation between competing manufacturers and military oversight agencies, with engineers sharing proprietary techniques and production methods in the interest of achieving technological parity with German aviation. The modified engines featured improved cylinder head designs that distributed thermal stress more effectively, crankcase assemblies with enhanced bearing surfaces that maintained lubrication under adverse conditions, and cooling systems with redundant heat dissipation capabilities that allowed continued operation even when primary cooling was compromised by battle damage. Each improvement was measured against combat performance data that tracked aircraft survival rates and mission completion statistics, with engineering modifications validated by the harsh mathematics of aerial warfare. By summer, aircraft equipped with modified engines were demonstrating survival rates that exceeded German aircraft performance in comparable combat situations, reversing the technological disadvantage that had cost hundreds of Allied lives during the early phases of the strategic bombing campaign. Bomber crews began reporting successful completion of missions that would have been impossible with earlier equipment, with engines continuing to function after absorbing damage that would have been fatal to standard power plants. Fighter pilots found that improved engine reliability allowed them to press attacks against German aircraft with confidence that mechanical failure would not leave them vulnerable over hostile territory. The cumulative effect transformed the mathematics of Allied air operations, reducing losses while increasing the effectiveness of missions that struck vital targets deep within German-controlled territory. The official recognition came quietly, without public acknowledgement of the unauthorized research that had started the process, as military bureaucracy preferred to credit institutional programs rather than individual initiative that had violated established protocols. Cornelius received a Bronze Star for meritorious service and a promotion that moved him to a staff position where his technical expertise could influence broader Allied aviation development, but the citation made no mention of the September evening when he had chosen engineering curiosity over military obedience. His commanding officer, Colonel Blackthorne, quietly admitted that insubordination had led to discoveries that saved more Allied lives than any single military operation. But he also noted that encouraging violations of orders could undermine the discipline that kept military organizations functional under the pressure of wartime operations. The modified engines became standard equipment for Allied aircraft operating over Europe, with production lines throughout the United States incorporating improvements that had been discovered through examination of captured German technology. Statistical analysis revealed that engine-related combat losses had decreased by more than 40% after the modifications were implemented, translating to hundreds of bomber crews who completed their tours of duty instead of becoming casualties of mechanical failure. Fighter squadrons reported similar improvements, with aircraft reliability allowing more aggressive tactics and extended combat operations that increased Allied air superiority over strategic targets. The knowledge gained from that single captured Focke-Wulf had cascaded through the entire Allied aviation industry, transforming manufacturing processes and design principles in ways that would influence aircraft development for decades after the war ended. But perhaps the most significant impact was felt by the families who welcomed home sons and husbands who would have died if their aircraft engines had failed during critical moments of aerial combat, lives saved by engineering improvements that existed because one captain had chosen investigation over obedience on a fog-covered morning in England. Captain Matthias Cornelius survived the war and returned to Connecticut, where he rejoined Pratt & Whitney as a senior engineer responsible for developing the next generation of aircraft power plants for the emerging jet age. He married his childhood sweetheart, raised 3 children in a house overlooking the same industrial landscape where he had learned to understand the relationship between precision manufacturing and human survival, and never spoke publicly about his role in transforming Allied aviation technology. His personnel file contained commendations for technical innovation and leadership, but the details of his unauthorized research remained classified long after the conflict ended. Letters arrived occasionally from former aircrew members who had learned through unofficial channels about the engine modifications that had saved their lives, expressing gratitude for work that had allowed them to complete missions and return to families they might never have seen again. One letter, from a B-24 pilot named Vincent Kowalski, described a mission over Ploesti where his aircraft had absorbed anti-aircraft damage that destroyed 2 cylinders and severed multiple oil lines. But the modified engine had continued running long enough to reach Allied territory where the crew could bail out safely. Another letter came from a P-51 pilot who had survived a dogfight with German fighters over Berlin, his engine continuing to produce power after taking cannon hits that would have been fatal to a standard Merlin power plant. These testimonials arrived sporadically over the years, reminders that engineering decisions made in secret during wartime had reverberations that extended far beyond the immediate conflict, touching lives and families in ways that could never be fully measured. Cornelius kept the letters in a desk drawer, reading them occasionally when he needed to remember why precision and innovation mattered more than following orders that prevented discovery. When he retired in 1968, his former colleagues honored him with a dinner that celebrated a career dedicated to advancing aviation technology. But none of the speeches mentioned the September night when insubordination had led to breakthrough discoveries that revolutionized aircraft engine design. The broader implications of Cornelius's unauthorized research extended far beyond the immediate wartime applications, influencing post-war aviation development and establishing principles that would guide aircraft engine design for decades. The metallurgical techniques he had discovered and adapted became standard practice throughout the American aviation industry, with companies incorporating German innovations into civilian aircraft that required the same reliability and durability that had proven essential in military applications. Commercial airlines benefited from engine improvements that reduced maintenance requirements and increased safety margins, allowing more efficient operations that made air travel accessible to a growing civilian market. The knowledge gained from examining that captured BMW engine contributed to advances in jet engine technology with heat-resistant alloys and cooling system designs adapted for the higher operating temperatures and stress levels associated with turbine power plants. NASA's early rocket programs utilized metallurgical processes that traced their origins to the German innovations Cornelius had reverse-engineered during those secret midnight hours in the Tangmere hangar. The military applications continued evolving through the Cold War era, with successive generations of fighter and bomber engines incorporating design principles that had been discovered through examination of enemy technology during World War II. Engineering schools began teaching courses that examined the relationship between materials science and combat survivability, using case studies that included the BMW 801 analysis, without identifying the unauthorized research that had made the knowledge available to Allied designers. The systematic approach to failure analysis that Cornelius had developed became standard methodology for investigating aircraft accidents and mechanical failures, contributing to improved safety standards that saved countless lives in both military and civilian aviation. Professional engineering societies occasionally published papers that discussed advances in engine durability and combat survivability. But the academic literature rarely mentioned that breakthrough discoveries had originated with individual initiative that violated official protocols. The human cost of technological advantage became apparent only through statistical analysis that compared Allied aircraft losses before and after engine modifications were implemented, revealing the true scope of lives saved through unauthorized research that had transformed Allied aviation capabilities. Before the modifications, Allied bomber formations flying deep penetration missions over German territory suffered engine-related losses that averaged nearly 30% of participating aircraft, with survival rates that made completion of a standard 25-mission tour statistically unlikely for most aircrew members. After modified engines became standard equipment, engine-related combat losses dropped to less than 15%, a difference that translated to hundreds of bomber crews who completed their tours instead of becoming casualties of mechanical failure over hostile territory. Fighter squadrons experienced similar improvements, with aircraft reliability allowing pilots to engage German fighters with confidence that engine failure would not leave them vulnerable during critical phases of aerial combat. The mathematical transformation was dramatic. Allied air operations that had been marginal undertakings with uncertain outcomes became systematic campaigns that steadily degraded German war-making capacity while reducing the human cost of strategic bombing. Individual stories emerged from unit histories and personal memoirs, describing specific missions where modified engines had allowed aircrew members to survive damage that would have been fatal with standard equipment. Staff Sergeant Raymond Kuznetsov, a ball turret gunner on a B-17 Flying Fortress, wrote in his diary about a mission to Schweinfurt where his aircraft's No. 3 engine absorbed flak damage that should have caused immediate failure, but instead continued producing enough power to maintain formation until they reached the relative safety of Allied fighter cover. Lieutenant Commander Patricia Holloway, a Navy pilot flying combat missions in the Pacific Theater, reported that her F-6F Hellcat had survived the encounter with Japanese Zero fighters that had damaged multiple engine cylinders, but the improved cooling system had prevented catastrophic overheating that would have forced her to ditch in hostile waters. These accounts multiplied across every theater of operations, creating a body of evidence that demonstrated how individual engineering decisions had influenced the outcome of countless combat missions. The irony of Cornelius's achievement became apparent only in retrospect, when post-war analysis revealed that his violation of orders had ultimately strengthened military effectiveness by improving the tools available to Allied forces fighting against technologically sophisticated opponents. Military doctrine emphasized obedience and standardized procedures as essential elements of organizational effectiveness, but innovation often required deviation from established practices in ways that challenged traditional command structures. The tension between discipline and discovery had played out in a darkened hangar, where one engineer's curiosity had overcome his respect for military protocol, leading to advances that saved more lives than any single battle victory. The captured Focke-Wulf had represented an opportunity that existed only briefly, requiring immediate action that could not wait for official approval or bureaucratic review processes that might have delayed crucial discoveries for months. Cornelius had recognized that technological knowledge was perishable. That understanding enemy innovations required rapid analysis before the evidence was shipped away to facilities where other priorities might prevent thorough examination. His decision to proceed without authorization had violated fundamental principles of military order, but it had also demonstrated that creative problem-solving sometimes required independence of thought that could not be achieved within rigid organizational structures. The success of unauthorized research had created precedents that influenced post-war military policy regarding technical innovation, with subsequent conflicts featuring provisions for accelerated development programs that could respond quickly to enemy technological advantages without waiting for formal approval processes. The lesson was complex. Individual initiative could produce breakthrough discoveries that benefited the broader war effort, but it could also undermine organizational discipline in ways that might prove harmful under different circumstances. The long-term legacy of that September night extended through generations of engineers who learned to balance respect for established procedures with recognition that innovation sometimes required courage to challenge conventional wisdom, when evidence suggested better alternatives were possible. Engineering schools began teaching case studies that examined the relationship between individual initiative and institutional effectiveness, using examples that included anonymous wartime research that had transformed aircraft engine design without crediting the specific individuals who had taken risks to achieve breakthrough discoveries. Professional development programs emphasized the importance of technical curiosity and systematic investigation, encouraging engineers to question assumptions and explore alternatives, even when doing so challenged established practices or violated conventional protocols. The aerospace industry incorporated lessons about rapid prototype development and accelerated testing procedures that could evaluate new technologies under realistic operational conditions, rather than waiting for laboratory validation that might not identify performance characteristics crucial to combat effectiveness. International conferences on aviation technology featured presentations that discussed advances in engine durability and combat survivability, sharing knowledge that had originated with examination of captured enemy equipment but had evolved into principles applicable to civilian aircraft development and space exploration programs. The scientific method itself had been vindicated by research that proved the value of careful observation and systematic analysis, even when such activities violated organizational rules that were designed to maintain order rather than encourage discovery. Universities began offering interdisciplinary programs that combined engineering training with instruction in ethics and decision-making, preparing future technical professionals to navigate situations where institutional requirements might conflict with opportunities for advancement that could benefit broader society. Today, modern aircraft engines incorporate design principles and manufacturing techniques that can be traced directly to innovations discovered through examination of that captured BMW 801 radial engine. Though few contemporary engineers realize that current technology exists because one captain chose investigation over obedience during a critical moment in aviation history. Commercial airlines operate aircraft powered by engines that utilize redundant cooling systems, stress-resistant alloys, and fault-tolerant designs that originated with German engineering innovations reverse-engineered during World War II and adapted for use in Allied aircraft through unauthorized research that violated military protocol. Military aircraft continue to benefit from advances in combat survivability that allow modern fighters and bombers to complete missions after sustaining damage that would have destroyed earlier generations of aircraft, capabilities that exist because wartime engineers had the courage to examine enemy technology and adapt superior techniques for use in Allied equipment. The space program relies on metallurgical processes and thermal management systems that evolved from techniques discovered during examination of captured German aircraft, with rocket engines and spacecraft components utilizing material science that traces its origins to those midnight hours when Captain Cornelius methodically disassembled an enemy power plant to understand how German engineers had achieved the impossible. Private aviation benefits from engine reliability and durability improvements that make flying safer for civilian pilots who rely on equipment that incorporates lessons learned through analysis of combat-proven German technology adapted for peaceful applications. The global aviation industry represents a trillion-dollar economic sector that depends on technological foundations established through research that began with unauthorized examination of captured enemy equipment, demonstrating how individual courage and technical curiosity can influence developments that benefit humanity for generations. Educational institutions continue to graduate engineers who learn principles of materials, science, thermodynamics, and mechanical design that originated with discoveries made through investigation that violated military orders, but advanced human knowledge in ways that continue to save lives and improve technology. The scientific community recognizes that breakthrough discoveries often require individuals willing to challenge established procedures when evidence suggests that better alternatives exist, even when pursuing such knowledge involves personal and professional risks. Looking back across more than 80 years, the captured Fw-190 serves as a reminder that technological progress often depends on individuals who possess sufficient curiosity and courage to investigate opportunities for advancement, even when doing so violates established rules or challenges conventional wisdom. Captain Matthias Cornelius made a decision that changed the course of aviation history, not through dramatic heroism on a battlefield, but through quiet determination to understand how enemy engineers had solved problems that continued to kill Allied aircrew members who deserved better equipment than their own industry was providing. His unauthorized research demonstrated that innovation requires both technical expertise and moral courage, the ability to recognize when existing procedures are inadequate, and the willingness to take personal risks in pursuit of knowledge that might benefit others. The lesson transcends military applications and wartime urgency, applying to any situation where established practices prevent investigation of alternatives that might prove superior to current methods. Modern challenges in fields ranging from medical research to environmental protection often require individuals who can balance respect for institutional procedures with recognition that breakthrough discoveries sometimes demand independence of thought that cannot be achieved within rigid organizational structures. The question facing every generation of engineers, scientists, and technical professionals remains fundamentally unchanged. When evidence suggests that unauthorized investigation might lead to advances that could save lives or improve human welfare, do institutional rules take precedence over the potential benefits of discovery? Captain Cornelius answered that question by choosing investigation over obedience, engineering curiosity over military discipline, and human welfare over institutional convenience. His decision in a darkened hangar during the autumn of 1943 created ripples that continue to influence aviation technology and serve as an example of how individual courage can transform entire industries when applied to problems that matter. Would you have broken the order to examine that captured engine, or would you have obeyed regulations that prevented discovery? The choice between institutional obedience and investigative courage remains as relevant today as it was during that September night, when one engineer decided that understanding enemy innovations was worth the risk of court-martial and career destruction. Comment below and share this story so others remember that technological progress often depends on individuals willing to challenge established procedures when human welfare hangs in the balance, because the next breakthrough discovery might require someone with the courage to pursue knowledge, even when doing so violates conventional wisdom or institutional rules.